Welcome back. Here we are with a very important discussion on stress and strain, and that is Hooke's law. Oh, that is a very small. So that's Hooke's law. What is it? Hooke's law. We discussed the stress strain diagram in the previous video as this one of the previous videos we discussed this graph. You have your stress on your y-axis and your strain on the x-axis. Now, for all materials, most materials, there is a certain period where the strain follows a linear relation to the applied force or the developed stress within the body. So you can see there is a straight line for most materials. It is not the same in cases of all materials. There are differences in the shape of the stress strain diagram for different materials. For brittle materials, that linear relationship holds true very near to the ultimate fracture point or to the ultimate tensile strength point. There is not that much difference from the linearity before the material breaks. Whereas for ductile materials, you can't really see that that region. You can see that it's hardly any linear relation on this curve here, and that applies for some organic materials like sand and wood and etc. as well. There is hardly any linear relation exist in these two cases. Whereas for brittle materials, pretty much that linear relation extends up to the fracture point. So there is differences. However, we can generalize this by saying there is a linear relation for every single materials, and this generalization allows us to develop a condition for Hooke's law. So we said strain is directly proportional to stress for all materials. Again, this is a generalization. There can be differences between the up to what point that linear relation can be applied. However, in all cases, there is a linear relation. So strain is directly proportional to stress, and you know that all proportionality constants can be changed to equalities by using a constant, and we use a constant constant here, which is E times epsilon, or your strain, and this constant of proportionality E is called Young's modulus, or elastic modulus, or modulus of elasticity. Elastic modulus, modulus of elasticity, or Young's modulus. It is called Young's modulus because it is so called in the honor of Thomas Young, an English scientist who described the modulus of elasticity in his book called Natural Philosophy, which is published in early 1800, and that's why this constant of proportionality is called Young's modulus. Now, you know the strain quantity, or the quantity of strain, is a dimensionless quantity because strain is change in dimension over initial dimension. In this case, the strain will not have a dimension, and therefore stress and constant of proportionality, elastic modulus, holds the same unit, which is in SI system it is Newton per millimeter square or Pascal, and US customary system it is PSI, pounds per square inch. It is the same unit for stress and Young's modulus. Now, there is one more thing we need to note here, and as I said, strain is a dimensionless quantity, and you also know that strain is a very small infinitesimal quantity. For an applied stress, the strain induced on a body will be very small, and therefore from this equation we can see because strain is a very small quantity, the Young's modulus must be a very high or a very large number. For all steels at room temperature, the Young's modulus, the value of Young's modulus is between 200 to 207 gigapascal, and this will vary for other materials. One more thing to note here is Young's modulus is the definite property of a material. It will not vary depending on the process or the application. That is a definite property, and for all steel materials, the value of Young's modulus is between 200 to 207 gigapascal at room temperature. This is a very important term, or a very important useful term that we use in most engineering calculations. So once again, to recapitulate, for all materials there is a point to which a linear relation exists between stress and strain. So you have a linear relation in brittle material very nearly up to the final fracture point, and you have hardly well, you can still see there is a linear relation for ductile and other organic materials. So to generalize this, we can say there is, for all materials, we have a directly proportionality or a proportionality exists between stress and strain, and symbolically it can be written as sigma directly proportional to epsilon, which is stress directly proportional to strain, and changing the proportionality to an equality, we can rewrite this equation as stress is equal to, using a constant, times strain, and this constant is called elastic modulus, modulus of elasticity, or Young's modulus. Strain is a dimensionless quantity, and therefore stress and Young's modulus holds the same unit, which is Pascal in SI system and PSI in US customary system. And once again, because the strain is a very small quantity, infinitesimal quantity, the value of Young's modulus is usually a big number. For all steels at room temperature, the value of Young's modulus ranges between 200 to 207 gigapascal. That is 200 to 207 times 10 raised to 9 Pascal. Once again, thanks for watching. We will continue this discussion in the next videos. Thank you.